So let me talk about the energy and climate change, the challenges and opportunities. Thank you very much. I'm going to very briefly mention what was really happening for the last couple hundred years. One of my favorite paintings, one of my favorite painters. This shows an iconic warship, the HMS Temeraire, being towed by a fossil-burning tugboat to its final berthing place where it's going to be chopped up for scrap lumber. And what you see is, I think what Turner was trying to capture was the end of a sailing era, beginning of powered boats and in a setting sun. And so this is one of the events that marked the beginning of the Industrial Revolution. There are many other things. But with the Industrial Revolution, we also have discovered in the last couple of decades there's some unintended consequences. And this is one of the certainly unintended consequences. This is a record from 1800 to 2011 of the average land temperature of the Earth. Now, let me go on record saying we don't understand many of the things on this graph. We don't understand all those bumps and wiggles. You'll notice between about 1920 to 1970, 75, 80, there's a long plateau. We're now in a little plateau. Since I've spent 4 or 5 years in Washington, I just want you to point out that people say, no, the climate's not changing. Clearly, you can see in the last 10 years, the temperature has not increased. But if you look over, that's a joke. The temperature has increased over the last 200 years. But the remarkable thing is only since the late 70s has it really begun to markedly increase. Now, I want to emphasize we don't understand these plateaus. We don't understand the bumps, the wiggles. But if you average over a half a century, we begin to understand it. If the brightness of the sun has not been changing, and there's good reasons to believe it has not, but there's direct satellite observations of the sun on all frequencies of the spectrum, the visible, the infrared, the sunspot activity, everything. The last 35 years, it has a solar cycle of 11 years, but the baseline has not been changing. And there's good reasons to believe that the sun has been quite stable over billions of years, and for the next couple billion years it will be stable. And then some bad stuff happens. But I won't talk about that. About 4 billion years from now, some really bad stuff will happen. So there's time to figure that out. The most important thing is over a long period of time, you no longer have to worry about the ocean currents, the energy interplays. It becomes conservation of energy. If the sun hitting the upper atmosphere of the Earth is constant and there's less energy leaving the Earth, then it can only do one thing. It can warm up. Now, I want to remind you of epidemiology. Epidemiology means you don't have a detailed understanding of something in, let's say, medicine. But by looking statistically at this to ensure that there's a true correlation, not a false correlation between this, you can discover a lot. So this is a record of tobacco use in the United States, 1900 to 2005. And so in the beginning of the 20th century, we were not a tobacco smoking nation, virtually no tobacco smoking. And as it went, it peaked around the late 60s, early 70s, going to average consumption per adult male of 4,500 cigarettes per adult male per year. It's pretty high because not all the population was smoking. But around that time, in the middle 60s, science had begun to say, you know, there's really strong growing evidence that if you smoke cigarettes, you have all sorts of issues, higher incidence of lung cancer, higher incidence of emphysema, all these things. And so this is the cigarette consumption in black. In blue are the male cancer deaths. And what was happening is it was increasing, there was a roughly 25-year delay from the time you started smoking to the time when you got lung cancer and died from it. So it was a little time bomb that was going on. And so in this 25-year delay, but you see in the middle 60s when the Surgeon General is saying, hey, we maybe should be reporting the dangers of cigarette smoking. And then in the 70s and 80s, a concerted effort to try to keep younger people, high school, grade school people from smoking. And what happened is the cigarette consumption went down by roughly 60%. And then 25 years later, the deaths went down. This is the record of female lung cancer deaths. It started later because females started smoking later. So this is epidemiology. We now know today that if you start smoking a half pack of cigarettes a day or so, you have a 25 times higher chance of getting lung cancer, which mostly is fatal if not discovered early. It remains fatal. You have a 2 to 4 times higher chance of coronary disease and stroke. It's the largest preventable deaths in the United States that have to do with health. If you take all the people in all the wars in the United States and compare it to the number of deaths, premature deaths due to smoking, smoking is a bigger number by tenfold. Okay, in 50 years. It's staggering. But you know, the tobacco companies are coming back and they're trying to increase market share with e-cigarettes and things. But never mind. That's another lecture. I'm going to talk about climate epidemiology. So in this, I'm using some data collected by a reinsurance company. For those of you who don't know, a reinsurance company are where insurance companies go to insure themselves. If there's a large disaster, they may not have enough liquid assets on hand to pay out the premiums, so they actually take out insurance. So companies like Munich Re and Swiss Re and all these companies actually want to track large financial loss disasters around the world. And so these are the natural disasters tracked in the United States from 1980 to 2000, half of 2013, but all of 2012. And they track earthquakes, they track storms, they track droughts, they track heat waves. Anything floods, they track anything which triggers an insurance loss. And so what you see here in the different colors are those events that trigger insurance losses, significant insurance losses. Earthquakes are the brown at the bottom. There doesn't seem to be much there in terms of any pattern, but the rest of it seems to be increasing. All right? Another fact, if you look at the biggest natural catastrophes since 1950, 3 of them were earthquakes, 1 in Japan, 1 in Los Angeles, 1 in New Zealand. The rest are storm-related, and the really interesting thing about this is 6 out of the last 7 of those storms occurred in the last 8 years. Over a 63-year record, the biggest insurance losses are only very recently, last decade. All right, so this is evidence that something as weird is happening to the weather. All right, remember when in the 60s, 50s, 60s, 70s, even into the early 80s, the tobacco companies were saying, look, we don't understand, you can't predict who's going to get lung cancer. You can't, there's no detailed molecular biology proof of what's going on. So it's an open question still, scientifically. But it really wasn't due to epidemiology by the 70s. I would say after a 35-year record of this increasing, the epidemiology, we can't predict hurricanes, we can't predict tornadoes, we can't predict whether it's going to be a bad hurricane season or a good hurricane season. But there's, and you shouldn't get excited about one season. But if you look over a 30-plus year record of weird stuff happening, that happens to be coincident with the biggest change in the temperature. That's epidemiology. Now, the trouble is, do we just say, well, let's wait and be sure for another 30 years, or do we want to start taking this more seriously? All right. Now, if you look at what might happen, so this is what has happened, and there are various scenarios that have been studied. A very aggressive scenario that we have not been following, will not follow, is in blue. And so, so what you have in this column here, this blue thing, you have another degree change. If you continue more or less in the same track that we're going, we are doing more efficiency. We are doing some reductions per unit GDP of carbon emissions, but you're heading in this direction. Now, Yogi Berra, who's the great American philosopher of the 20th century, he said many great things like, you know, if you come to a fork in the road, take it. You can see a lot by watching. He did not say this, but he should have. If we don't change direction, we'll end up where we're heading. So this is where we're heading. And this is going to be, by the end of the century, this will be maybe an additional 4-degree increase. Now, 4 degrees centigrade, you know, is that a big deal? You know, weather in Chicago changes by 25 degrees centigrade, at least 20 degrees centigrade in one day. So you guys are all wimps, climate wimps. But this is a record looking back 800,000 years. This is the present time over on the right-hand side. And what you see is a kind of a warm period, and then there are cold periods. So these are the ice ages. And the ice ages were about 5-6 degrees colder. Now, average temperature 5 or 6 degrees colder, what did that mean? It meant all of Canada and half the United States covered year-round in a glacier. That's 5 degrees. So 5 degrees hotter means an equally different world. All right? Now, one of the things is these transitions, you know, this repair. The other thing this shows you is, first, humans didn't cause this, you know, these changes in temperature. They were actually triggered by slight changes in the orbit and the tilt of the Earth, the eccentricity of the orbit and the tilt due to perturbations of the other planets. What is not understood is why the change was that big. It should have been 1/10, 1/20th, a teeny tiny little fraction. And so what this tells us, and there's other, if you go back even further, what it tells you is that the climate is really hypersensitive. So little changes in things can actually change things. And then you can look at this and say, well, why are we worried about global warming when there's an ice age? And say the issue is over here on the far right-hand side in the upper curve, you can't even see it, it's a vertical line. This is the change in carbon dioxide had just shot up by about 45%. You know, in geological time scales, it just all of a sudden you're off the scale of what happened in the last 2 million years. So those are risks. You know, in this period of time over here, there's estimates that the sea level was about 6.6 meters higher. Right? So it's a little higher. A lot of airports around the world will be underwater, and I think Stanford is marginally safe. We may have shorefront property or something. Okay, here's something else. Let's model, you're going along in different emission scenarios, but at 2300, their greenhouse gas emissions around the world due to humans absolutely stops. Now, you can be very aggressive control of this, so this is the atmospheric CO2, or you can be business as usual. And this is the temperature, and this little blurb downward is because the greenhouse gases like methane actually get converted to carbon dioxide. Methane breaks down in the upper atmosphere. So, but then you notice something. There's a long plateau. What's the scale? This is year 2000, this is year 3000. So the temperature rise then only subsides very slowly over many thousands of years, at least 2,000 or 3,000 years. So whatever we're going to do, it's going to last for a long time. This band over here is in this danger zone. At that point, the bad news is Antarctica will be melted. The sea level is about 60 meters higher, 200 feet higher. It will take several hundred years to melt. For those of you who read the New York Times and the articles, there's at least a little part of West Antarctica that's going to be rushing out to sea. So, but the issue here is it takes a long time. So let me return back to epidemiology. As we do this, we don't know what the damage to our environment has already been done, because it may take 50 years, may take 100 years to find out what we've already done since the beginning of the Industrial Revolution. Now, if you smoke, the smoker pays the consequences of smoking. But suppose you have grandchildren and you smoke, and there's a considerable risk that your grandchild will get lung cancer or emphysema or stroke or heart disease from your smoking. Not you, but your grandchildren. Chances are you would try very hard to stop smoking, right? You smoke, okay. But here we are in a very strange state. Not only our grandchildren might suffer the consequences, but their grandchildren might suffer the consequences, and their other grandchildren, okay? Thousands of years of grandchildren will suffer the consequences. And so far, society has said, this is not our problem. Okay? We smoke. People I won't even know 1,000 years from today. Not my problem. So this is a problem because, now why are we being so callous about this? It's because, quite candidly, we're in a new sociological situation. Under no times in the past where science has said, what we're doing today will affect what will happen 1,000 years from today and 2,000 years from today. So it's a new social adjustment to actually try to understand that that might be true, that there are risks. Exactly what will happen, we don't know. The uncertainties are very big. But already from 0.7 degrees centigrade increase, the weather's getting weird. So, and we know that at 5 degrees centigrade or 6 degrees centigrade, Antarctica melts, and the weather will be unrecognizable. Okay? So that's what these are the risks we're playing with. Now, you could say, not a problem, we'll run out of fossil fuel, we'll run out of oil and gas, especially in that. So I want to quote two authors I respect immensely. And they said, our ability to find and extract fossil fuels continues to improve, and economically recoverable reservoirs around the world are likely to keep pace with the rising demand for decades. I wrote that. With Arun Majumdar, who's coming to Stanford this fall. And so why were we saying that? Well, this is a record of U.S. oil production 1945 to 2012. And it peaked at, around 1970, and it started to decline. This is the orange, or whatever it is the Alaskan oil find. And even with the big oil in Alaska, it did not stop the decline. And the far right, you see this little green wedge. It says tight. That's tight oil. This is horizontal drilling, hydraulic fracturing of rock to release oil. And so it started to increase. And in 2013, we're up to 7.5 million barrels a day. And by the end of 2014, we'll add another 1 million barrels a day. The amount of oil recovered from just the hydraulic fracturing is more oil produced per year than any other country in the world except Saudi Arabia and Russia. Bigger than Iraq, bigger than Iran, bigger than Libya, bigger than every other country. That's the increase in oil production. Okay. What about natural gas? This is a prediction made by a company that prides itself in accurate forecasts, made in 2008. This, on the left-hand side, is the gas production from various sources. On the right-hand side, a forecast of declining production of natural gas. They got it wrong. That's what our natural gas production is by 2013. It did not go down, it went up. Another thing, if you look around at these formations and you ask what is economically recoverable, let's say at $80 to $100 a barrel and what at natural gas prices, it turns out that the rest of the world might have 10 times as much oil and natural gas reserves in these new sources than the United States. So we're not going to run out. There's enough carbon in the ground in coal and oil and natural gas to really cook us. okay? We won't run out this century. There will be no peak in declining oil, at least for the next 50, 80 years. So I'm reminded of this quote of a Sheikh Yamani, and he said, the Stone Age came to an end, not for the lack of stones, and the oil age will come to an end, but not for lack of oil. It was actually said by a former Saudi oil minister. That's not why he's the former Saudi oil minister. And what is unsaid is that he was thinking we transitioned to better solutions. So in the Stone Age, we went to copper or bronze or other things. Lots of stones around, but we went to better things. So what are those better solutions? So let me talk about a few. Let's start with energy efficiency. And it was mentioned that I was doing a little study on appliance efficiency. These are all physicists or former physicists. And we asked the question, if you do appliance standards, it's always expected that the price of the appliance will go up, but you will save money because you're going to pay less for the operating expenses. So we said, all right, let's look at the historical record before standards started in California, which led the country, followed by national standards. What was the price of owning a refrigerator, which is purchase price and energy costs, and what was the price of purchasing the refrigerator? So the open symbols, the blue is the total operating costs and purchase price, and you see that when you go to the solid symbols, the first California standard started, and followed by 2 more standards of California, followed by federal standards. And so clearly you see a market change as you double productions. It used to be declining by a certain fraction per unit doubling. That's called the learning curve. But when we went to standards, all of a sudden the learning got much better in terms of the cost of ownership. And here you see the cost of the appliance. Oops, it didn't go up. It kind of remained the same. And if anything, it might have gone down, okay? So that was a little bit unexpected. So this is over, from 1950 to the present time. We looked at room air conditioners. The cost of owning and operating the air conditioner plummeted. Well, look what happened. The cost of the air conditioner went down. That's known as a market failure. Why would, when you make a regulation that said you can only produce air conditioners that have to be above a minimum standard, why did they get cheaper? They should have gotten more expensive. And what you can theorize, I'm an experimental physicist, but you could wave your hands and say, well, maybe the engineers made more efficient compressors, and that means it didn't have to be as big a compressor, but that's theory. So we looked at room air conditioners, we looked at central air conditioning, the same thing. We looked at clothes washing machines, the same thing. We looked in Europe, the same thing. Appliance standards actually drove the price of the appliance. It either remained the same, it didn't drive them up, or it actually drove them down. Remarkable. So what economists will say when they look at this is, this may work in practice, but it doesn't work in theory. So that's some of the reception we got. So therefore, you can't publish it. It's been a long to be published. So now here's something when I was Secretary of Energy I really wanted to start to regulate, to put an appliance efficiency standard. And this has to do with cable TV or box-top sets of satellite TV. There's those little boxes that you put on, and it takes the digital signals and decodes it and puts it onto your TV. And those little boxes, if you notice, are kind of warm. Now, they're kind of warm all the time, even if you hadn't turned it on all day. It's because when you think you've turned it off, you've turned off the little display in front, but the electronics are still on. Now, then in December of 2013, I get a little note from a former public affairs head, and he said, Steve, you must be very proud. We've now got an agreement from the pay television industry that says we're going to reduce the energy consumption of these boxes by 10 to 45% by the year 2017. I wrote back and said, that's really disappointing. They waited me out. What was I hoping for? I was actually hoping it would go from 30 or 40 watts to about 1 watt or 0.3 of a watt. Now, let's think about why, and I was explaining to them why you can do this. If it's not on, if it's on standby, they say, well, you need to leave it on because you have to download programming information. So I said, well, no, put a crystal oscillator in the little device, like the kind on your watch. You know, a little teeny battery can go 3 or 4 years, so there's no power there. You wake it up for 5 minutes, you download the programming information, you put it on flash drive, and then, which doesn't take any more electricity either, and then it goes to sleep again. The only thing you have to keep on is a little infrared sensor with an interrupt system. Every 1/10 of a second you say, is anyone talking to me? Okay? That's about 100 milliwatts, 1/10 of a watt to do that. The rest of it's off. Memory cost, I don't know. You can't price 100 kilobytes of memory. That's all you need for a day's programming. So, you know, I don't know how, you know, this is, you know, the prices start at 1 gigabit. Now, why don't they do that? Because they like to reuse their old electronics. I actually learned this from our cable installer. They want to take those old cards and they'll put them in a new case, and they sometimes give it a new model number, but it's the same old electronics. And they don't have to reprogram anything, okay? Because they're not paying for the bill. How much is the bill? Well, 100 watts, you got 3 of them, and I'm taking the low end. It's more like 150 watts. If you have a recorder, the digital recorder, the hard disk is always spinning. They don't even turn the hard disk off. It turns out to be, if you're paying 15 cents a kilowatt hour, you're paying about $130 more per year for electricity. If you multiply by the number of customers in the United States, 90 million customers, that's $12 billion. If you say, how much energy are you saving? Well, it's equal to 10 1-gigawatt nuclear power plants, or more than all the coal plants in Ohio, just to keep the set-top boxes on standby, okay? You can do an experiment. You know, when you go out and you travel, you turn off all the lights. Your refrigerator usage is about 40 watts. It's equivalent to 1 set-top box. So you got 3, if you got 4 of these set-top boxes, you got 5 refrigerators in your home. You may have 2 refrigerators, but at least you know they're refrigerators. And eating up energy. But so it was sad. This is one of the reasons why I wanted to say Secretary of Energy. My wife had other ideas, but I really wanted to see if we could regulate this. There's no market pressure for the people to change, right? You're not picking your cable TV because of the energy of the set-top boxes. Another thing that this is a positive good news, a consortium of companies, because voluntarily got together and said, if you look at internet traffic, if you look at mobile data, if you look at all of this stuff, which is consuming about 2 or 3% of electricity in the United States today, if you go on the course where technology we're going on today, it could go to well over 10% to 15% of the electricity. When you go from 3G to 4G to 5G, not on your phone, but in the transmission, and in the data centers, and the cloud computing, and the little computer in the cloud that's telling Siri what to say to you. It's that stuff. And so the good news is the industry leaders formed a consortium and said, called Green Touch, and said, if we design this right, you can get the higher bandwidth, you can have all this other stuff, and you can keep the electricity consumption the same. So that's where there's some leadership going on. Now let me turn to clean energy sources. These are good news stories. Wind turbines have gotten much better. The levelized cost of electricity of land wind in a reasonable site, not the best sites, is now about 7 cents a kilowatt hour. And it's expected in the next 10 or 15 years that the price will decline 20 to 30% more. The actual contracts being signed by the new wind farms. So this is what's called a power purchase agreement. The developer builds a wind farm, and they enter in a contract with the utility. We will supply you with electricity, and you will pay us this amount for the next 20, 25 years. Depending on where you are, if, for example, if you're generating wind in the Dakotas, Kansas, Iowa, the contracts now being signed for delivery are getting to be about $30 a megawatt, 33 cents a kilowatt hour, which includes the profit of the investors. Okay? This is far cheaper than a new coal plant. If you're in less desirable sites, it can be 40, 50, 60 cents. So these are contracts now being signed. Now, there's a production tax credit subsidy, and I'll get into that in just a few more slides, to try to adjust for, if you get rid of that subsidy, how much would you be paying? Solar, also very good news, another learning curve. Every 10 times deployment, the thing goes down by a certain fraction. There was a 2015 production that the cost of a solar module of a certain output would be $1. It didn't do that. There was an abundance of overinvestment, particularly in China, so the price plunged. A bunch of companies went bankrupt, including the biggest solar company in China, the biggest in Germany, and one in California. So a bunch of them went bankrupt. The price has gone up to that, but it's here now. It's going to be going down to here. By that, I mean that the manufacturers of the solar modules say, if we can't sell in the next couple of years at that green dot 50 cents a watt, we're going to go out of business, which means you have to produce at 30 cents a watt. Production costs are now about 50 cents a watt. Okay, so. And they're big, you know, the companies that are survived look like they're going to survive now, the ones that are still standing. So that's good. So the price has gone down 25 times, maybe 30 times. That's pretty good. It's like a $30,000 car costs $1,000. The solar electricity generation record from 1985 to 2013 kind of simmer along, and all of a sudden decided to skyrocket. What happened? That's it's no, I got a lot of heat for Solyndra, but in actual fact, many solar companies have done well, but the installation has done remarkably well. And so a lot of hundreds of megawatt projects have gotten started. The good news is that once you've demonstrated you can erect a couple hundred megawatt project in solar or wind, and you can build it on time, on budget, what happens is the financial community says, oh, that might be a good, safe investment. Because when you build it, before you build it, you have a power purchase agreement. And so that has, as Warren Buffett and others said, this is now bankable, and Warren Buffett actually owns some solar farms. Okay. So it now is viewed as a reasonable investment, and so that actually decreases the price of solar again, because now you don't have to spend as much to borrow the money. You know, if it's a risky investment, you want a 20, 25% return on your capital, but now you might be happy with 15% return over a long period of time. At least I would be ecstatic if I could get 15%. We have very ambitious goals for solar. Residential solar would be twice as expensive. Our goal for solar, for levelized cost of electricity, again, would put it in the ballpark of new natural gas. If natural gas costs somewhere between $4 and $6 an MMBTU. So those are historically low prices. They're in that range today. So if it stays in that range for the next couple of decades, renewables will still catch up. Residential solar in Germany costs $2.50 per watt to install. Per watt means a certain amount of sun hitting the solar panel. So it's talking about the efficiency size of the solar panel. It doesn't talk about where the panel is. And in the United States, it costs twice that much. You ask why, because solar modules are an international price within 5 or 10%. And the first thing you say is, oh, German labor is so much cheaper. Not. The German labor spend 1/3 of the time on the roofs. We actually started filming German installers versus US installers. And so this is a technology I think the United States can learn. How to get more efficient in installing stuff on roofs. There's all sorts of other things. This is with and without the subsidies. This is utility scale solar. This is with the blue is with the investment tax credit. The dark blue is without the investment tax credit. This is onshore wind with and without. This is new natural gas. It's the cheapest if there is no onshore wind subsidy, but if you say that we're subsidizing for the cost of carbon, it is no longer the cheapest, but wind is going to catch up even if you don't include that within a decade. That's all good news, including transmission. So the good news is fossil is actually becoming competitive, and in a decade or so, it will become the low-cost option. So why aren't utilities focused on saying, if you see this coming, let's plan for it? Okay, so here's one of the issues. If you're a utility company and you can flick on a switch and say, turn up a gas turbine, turn up the coal plant, or whatever, it's a lot easier to do that than to say, well, if I got renewables, I have to track if the sun is going to stop shining or if the wind's going to stop blowing. I have to coordinate a lot of things. So going as business as usual means you don't have to think very hard about this. We know we've been doing this for 100 years. And you know, most utility companies are not known for their innovation, that they move at glacial speeds in adopting new technologies. But that's really, oops, that's really unfair to glaciers. Glaciers are beginning to move faster, especially with climate change. Now, let me give you an example of what we're up against. In the Recovery Act, we actually invested $3 or $4 billion to give to the utility companies instruments that can measure the phase of their local distribution supply. So you look at the phase and the power. And why is this important? Because if you wanted to coordinate across different districts, you want to know this phase and what's happening. The massive blackout in the Northeast that had about a 30-minute precursor of things getting out of phase that said something terrible is happening. But we did not have automatic means of logging this in, and they weren't installing them, and so we said, okay, we'll give them to you. So we're going to give you these things so you can begin to coordinate the grid better, and so you can tolerate. It means better grid reliability. It means you can figure out what's going on. And these are some balancing authorities. And then for the first year or two, the companies who got these instruments didn't want to share the information with the other companies. So I gathered them up in a conference room in Energy. I said, this is terrible. He said, no, it's proprietary information. He said, for the sake of grid stability, you've got to share them. You got them for free, for gosh sakes. And so at least there's some movement. But the thing is, so they can measure the phase, but the information network transfer is being done. It's being paid for largely by the Department of Energy. There's an opportunity, a business opportunity here, by the way, because the sharing of this phase information, the sharing of where the energy is needed allows you to do much more efficient energy arbitrage. All right. So the reason renewables is harder is because you have to integrate renewables with on-demand energy sources, energy storage, transmission, distribution. So let's look at what you can do. The Department of Energy has some authority over some of the wind farms, and if you put these anemometers, those things that spin, and you put them a couple miles out, you can actually track and you know what the wind is going to change. You actually are allowed to use weather reports as well, but in fact, in the modern generation wind turbines, they're beginning to use Doppler radar to look ahead, right? So you're going to get a 10, 15-minute warning of the wind is going to change. And they're beginning to use those so they can feather their blades so they can have optimum power. Right? That's why the wind turbines have it. But it also gives you a 10 or 15-minute warning, or a 5-minute warning for sure. And then you have batteries. I'm going to talk about it in a moment. But you also have fast ramping natural gas and hydroelectric power. Now, hydroelectric power responds in a few minutes, except for one thing. It's not automated. You got to water in a dam and you say, wait, you want a little burst of power, you open the spigot a little bit. Except it's not automated, so you have to call up the dam operator and say, hey, Joe, can you open the valve? No kidding. Okay? So we have to get out of the previous century and begin to say we want to automate these systems. We want to automate how we can move electricity around with automatic digital relays rather than sending a truck out and say, where's the line down? So this is just beginning to happen, only in the last decade, half decade. This is a modern natural gas plant in California. Each of these, they're dual, each of them can ramp up 50 megawatts per minute with 60% thermodynamic efficiency. So that means the new natural gas turbines, they are built to actually ramp up and down many times a day because they're really designed like jet engines. You go from simmering to full throttle back to simmering. So it's technology like this that is absolutely vital for integrating with renewable energy, either sun or natural, but we have that. So each of the pieces we don't have the system yet. Let's talk about batteries and energy storage. And I put storage in quotes because it can become in wide forms. Here's a novel thought. When the wind blows, pump water. That's energy storage. You might look at that. That's what we did 100 years ago. we pump water from the ground when the wind blew, and then it's up there for use. Not when you want it, but when you put it in a tank. So that's a form of energy storage. Another form of energy storage. This is a picture of the Texas Medical Center cogen plant. It generates electricity and it generates process heat. Now, it's in Texas. It's in Houston, I think, or Dallas, some really hot space. I think it's Houston. And you don't want heat. You want air conditioning. And so this is a big tank of water that they chill at night. And they use it to run their air conditioning system in the daytime. Stanford is actually building a cogen plant, a new one. And if you look at it, there are two big tanks of water. That's energy storage. Okay? So this is out there. Normal batteries, in 2008, if you built a battery for an automobile, the manufacturing cost is about $1,000 a kilowatt hour. In 2012, the cost was cut in half. And in 2011, we set a goal. Let's look at realistically what you can achieve by 2022. And an ambitious goal was drop it another threefold. And if you drop it in another threefold, you can have a $25,000 car that goes 300 miles, and it just becomes the low-cost option for transportation. Similarly, if you go to 100 kilowatts hours cost manufacturing for utility scale batteries, it becomes a low-cost option for many, many things. By the way, if you achieve these goals, each of them will be a $100 billion a year business. It's real money, too. How are we doing? Well, this is Bloomberg New Energy Finance. This solid curve is Bloomberg's prediction of what battery costs for electric vehicles will be, and these red X's are the actual production costs. So it's very comforting to see that the red X's are on target for what we were saying would happen. Okay? And it was exceeding all the predictions from the internal combustion engine manufacturers. There was a very high-ranking engineer of a nameless major automobile manufacturer in the United States who said, batteries are never going to improve. They haven't changed in 20 years. They're not going to change in the next 20 years. He said it with such authority. It was amazing. We were in a little group, and he said, and I said, holy cow. He did not know what happened in the last 10 years. But he was, very scary. So it was mentioned in the ARPA-E, Advanced Research Projects Agency for Energy. And there it was an agency that was designed to swing from the heels and try to sponsor game-changing research that could lead to private sector adoption. High-frequency electronics, that would mean a 70,000-pound transformer could be 100 pounds, and you could transform a lot of power electronics. Really inexpensive batteries. to bring down the cost of battery storage to the cost of hydroelectric storage, which then you can put everywhere. That would be great. One of the companies we sponsored for the high frequency, high voltage electronics, 2 years after, we only give grants for 2 or 3 years, and they said after that, you're going to have to go find some money or do something. And so this little thing on the tip of a finger is a transistor that's a 1 megawatt, 12 kilovolt transistor, okay, without the heat sink. The heat sink's the size of your hand, but the fact is, this is the type of electronics, and that's a prototype. After 2 years, they were able to do this. This is the type of electronics we will need for the grid of the future. These are electrically things where you can actually port the electricity here or there, and you can direct it. Just as you can send information in little packets to your home, to whoever's you're emailing to, we now have the technology to send power that way. Except we need to get the utility companies and the distribution and transmission companies to adopt this. This is a picture of Europe's plans for underwater high voltage power transmission cables. But why do they want to do this? Because the wind resources of Ireland and North Britain and all around this region of the western part of Europe are tremendous. The hydro storage capacity of Norway and Sweden are tremendous. And so you want to link these up so you can bring wind into Europe. You want to bring energy storage back and forth between the continental Europe and these places. And so you need these underground high voltage DC, which needs better electronic switching to bring the cost down. But we're doing that. They're doing that in Europe. We have a few DC transmission lines. The Chinese are the world leaders in high voltage DC transmission. They're actually the world leaders in modernizing the grid to deal with renewable energy. And they are the biggest installers of renewable energy in the world in their country this year and last year. They're trying to, actually it's because the leadership believes that the climate's changing. It's caused by humans. Batteries, I'm just going to say that utility scale batteries are developing, there's major investments. GE's invested $250 million, startup companies. So there are major investments. I'm not sure when they're going to work. The requirements are very strenuous. They've got to work for 30 years with very high reliability. But the companies are targeting this price of manufacturing costs at $100, $150. So when they'll occur, I don't know, it'll be 5 years, 10 years, 15 years from today, but it'll be in that time scale. It's not 30 years from today, or it's not 20 years. All right, so solar is getting really inexpensive. Batteries are getting real expensive. Germany installation is now $2.50 a watt. The Department of Energy goal was quite modest. Can we install in the United States for $2 a watt? If you look at the price, when we reach these goals 5, 10 years from today, you can buy an 8 kilowatt, I forgot to change this, an 8 kilowatt battery system and 6 kilowatts of generation for under $15,000. Most of the solar in homes in California, you don't buy. You get First Solar or other companies to install. There's no cash up front. You enter into a power purchase agreement. The company owns, operates, and maintains the equipment, and you just buy electricity. A week ago, I talked to someone in Los Angeles. He just signed a purchase agreement with no cash out of pocket. He's just buying electricity, 9 cents a kilowatt hour. They go up there, they install it, and that's it. And with batteries, it's going to get really better, all right? So all this is coming down the pike. So I think this technology could be as disruptive to electricity generation distribution as the internet was to publishing and entertainment. So the last 2 years as Secretary of Energy, I gathered the regulators and the utility people and said, look, this is what's happening technically. These are the learning curves. And this is what they're researching on. So the chances are that's going to continue for a decade or two. It's very exciting stuff in all these areas. So let's try to design a better business model. Because otherwise, what will happen is more and more customers will just generate locally and take less and less of your electricity, which means it drives the cost up for everyone else. So I said, why don't you do the following? You go and offer a customer. You can partner with Sunrun or SolarCity or other people, and you go to you knock on the door of either a home or a business and say, let us install solar on your warehouse rooftop or on your sun. We will own the solar equipment. We will own the battery. We'll put it in your garage, a little corner this big. And if it breaks, don't worry. We'll fix it. We're just going to sell you electricity for slightly less money. Okay? A new business model, right? No, it's an old business model. The phone company used to own your phone. They were selling you phone service. Now, what's in it for the homeowner? Well, you get lower electricity rates. You get an 8-kilowatt local storage, which is about 5 days of blackout immunity. You can keep your refrigerator going, one refrigerator, 8 to 20 cubic foot refrigerator. You can, if you have CF, compact fluorescent lights, you can keep it, you're all lit up for, you can't turn your air conditioner on with this, and you might have to unplug some of those set-top boxes. But you're good for 5 days a week without rotting food. That's good. What does the utility company get? It gets indoor energy storage. It's out of the rain, it's out of the heat, it's out of the cold. And it's in exactly where they want it, at the ends of their distribution system to manage load surges. Okay? And they are in a growth market instead of a shrinking market. And so they can go to their stockholders and say, this is now a growth industry. If they don't do this, they will get FedEx to death. What FedEx did to the post office, which is skim off the best customers, the ones who pay their bill, right? Because it's the ones who pay their bill that would think of installing solar in their rooftop and a battery in their garage. So while I was Secretary of Energy, we started a number of new things, RPE, Sunshot, which is revitalized photovoltaic and also thermal solar, and EV Everywhere, that's the electric vehicles, the batteries. And during this time, I was able to recruit half a dozen people in the National Academy of Engineering and Sciences to come and work in the Department of Energy. So it went from 0 to 6 or 7. And another at least half a dozen young people who will probably get in the National Academy of Sciences and Engineering. Of the ones that came in who were already in the Academy, 2 or 3 got elected in their 40s, but they were still in their 40s. Okay? So we could actually bring in true stars in industry and academia to work in the Department of Energy for 2 or 4 years. And when you get true stars to do that, and then they help bring in more people, then you begin to make wiser scientific decisions. And so that was very important to me. That was what I was most proud of. And then when you bring them in, you can't let the bureaucracy drag them down. So you have to block it. So I spent most of my time blocking and tackling for these stars. And I used to say the greatest danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. That was actually said by Michelangelo. Now, so I was very proud of being able to attract some really talented individuals and say, come help serve your country, help serve the world. You have technical expertise, and we need people like you to make the decisions on what to fund. The part I hated the most, liked the least, was the press. They always are trying to play gotcha and make news. There was other parts I didn't like, but in February 1 of 2013, I was allowed to make the announcement that I was stepping down as secretary. I had told the president mid-November that after the election, he lined up all his cabinet members and started talking to him privately and said, well, what do you want to do? And I said, well, Mr. President, I really enjoyed serving with you, working for you, but my wife said, after 4 years, You know, it's time to head back home. No one's irreplaceable, and I'm going. So, and then in 6 days after I made the announcement, a news article came out, and it said, hungover Energy Secretary wakes up next to solar panel. So let me read you this. Washington. Sources have reported following a long night of carousing at a series of D.C. watering holes, Energy Secretary Steven Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening. According to sources, Chu's encounter with the crystalline silicon solar receptor was his most regrettable dalliance since 2009, when an extended fling with a 90-foot wind turbine nearly ended his marriage. So I walked into work, so my public affairs says, we have to respond to this. I smiled, said, you betcha. So at noon, we released the following statement. I just want everyone to know my decision not to serve a second term as Energy Secretary has absolutely nothing to do with the allegations made in this week's edition of The Onion. While I'm not going to confirm or deny the charges specifically, I will say that clean, renewable solar energy powers a growing source of U.S. jobs and is becoming more and more affordable, so it's no surprise that lots of Americans are falling in love with solar. And there were limits that he said, and you know, regardless of just sexual persuasion, no. So that was a lot of fun. Now, I want to go back to this picture that was at the beginning of my talk. This is Earthrise picture from Apollo 8. This is the first Apollo mission that orbited the moon, and the last of the orbits, they turned the capsule earthward, and one of the astronauts took this picture, and he said, we came all this way to explore the moon, and the most important thing is we discovered the Earth. Now, since Christmas Eve in 1968, very compelling evidence that the climate's changing, mostly caused by humans. And there are big risks. And so one has to look at this picture and look at the bleak moon, and it's not a good place to live. And from this vantage point, the Earth looks really very nice. And notice what else? There's nowhere else to go. Now, I'm going to skip this. No, I'm not going to skip this. I'm sorry, I'm going to make you wait a little longer. If you plot the prosperity of a country with three markers, education, health, and GDP. And it's called the Human Development Index. And you plot that versus your ecological footprint. How much land do you use? How much energy do you use? How much of the Earth's resources do you use? What you find is after a certain, you plateau. Japan and Denmark are over here. Norway and Canada is over here. Here's the US. We're way at the end. And so we happen to be using a lot more of the Earth's resources because we eat a lot of meat, we use a lot of energy. All right. If you do energy efficiency wisely, you don't have to sacrifice your standard of living. Is it possible to get over here? What about this red line is the current estimate of how much Earth you need to sustain this certain economic prosperity at a certain level. But that may not be true because technology improves in that respect also, and we don't know where that is. Let me just say very simply, we don't know where that is. As one example, the amount of land put on a grain production until very recently, when the population went from 3 billion to over 6.5 billion people, the amount of land put on a grain production remained the same, but the productivity around the world went up fourfold. Okay? So if you were making a prediction of that in 1960, you would say that's the limit of the Earth's production. So it just went up fourfold. Now, we're now putting much more land under production, but it's for animal feed. For the developing countries getting rich, they want to eat more meat. But then they will have to discover if you eat too much meat, it's really bad for your heart. But anyway, so we don't really know where these limits are. But I want to finally end with even a further point of view. This is a picture taken by Voyager 1, which is flying by the planets. And it would fly by Saturn, Neptune, Uranus, and it would take pictures of these planets. And as it was leaving the orbit of Pluto, Carl Sagan convinced the NASA engineers to turn the satellite and find Earth and take a last little picture of Earth. And so I'm going to play with Carl Sagan narrating. Oops. Is there any sound out there? Hold on just a second. You guys.
That's us.
Thank you.
On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on the mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
I think we have a moral responsibility for those who are truly the most innocent. They're the poorest people in the world, had nothing to do with this, and literally 100 generations that will follow us, those yet to be born. And there's an ancient Native American saying is, we do not inherit the land from our ancestors. We borrow from our children and our grandchildren. Thank you. I'd be happy to take questions. There's microphones, but if you can shout out, but there's microphones for those who want questions, but yes.
Did you ever get a chance to make such a presentation to the U.S. Congress?
No. You know, you probably read in the papers, and it's very sad but true, that many people the wise political heads might say climate change doesn't pull well. Now, I would say the president absolutely agrees with me, but I think he also gets reined in by some of this. And it is, it's not high on the list of things. Jobs are high on the list. But there are real costs at work here. And quite candidly, the retrofitting of America to have a much more efficient building infrastructure are jobs that actually will save money. So that part, I think, there are jobs. And I hope there are people on both sides of the aisle. This should be a nonpartisan issue. Forget about bipartisan. Politics should not be in this. And as I tried to indicate, this is becoming the low-cost option. You just have to think a little harder. Okay? It becomes a low-cost option, but you have to think a little harder. And so that's what universities are for.
Thank you. Thank you for an inspiring talk. I'm still really pessimistic. And given that, I just wanted to ask you whether, considering the odds, I think it's actually morally irresponsible not to advocate strongly for the simpler geoengineering techniques. Although I know that that won't stop the carbon accumulation, it can stop the accelerating effects, which probably are the worst things that we have to avoid. We'll probably end up doing geoengineering in the end, but we'll wait until we have already accumulated accelerating effects such as glaciers, melting, methane increase, and all kinds of other problems that will make things more difficult. So I'd like you to comment.
Sure. First of all, we've been doing big-time geoengineering for a long time. It's called agriculture. If you look at what land we produce for grazing and for agriculture, it's a considerable part of the non-desert, non-mountain part of the world. There are certain parts of geoengineering I'm all for. As you know, I'm a big proponent of white pavement, light pavement, and white roofs. Okay? That reflects sunlight back into space. It becomes widely adopted in the middle part of the world, including much of the United States, it not only saves in electricity, but that's geoengineering. It becomes actually a significant fraction. I think reforestation is geoengineering, just as deforestation was. I think there should be research done to try to help both crops and forests mineralize more carbon faster. The things of geoengineering like sulfur dioxide, there could be unintended consequences. But long before you get to that, all these other things are probably pretty safe.
But those are slow movers.
That's true. But in the case of sulfur dioxide, you could change, we know from volcanic activity that you can actually affect it. But we also know that eventually the stuff comes down and makes acid. Right, but I'm just saying those are slow movers, but they're decade movers. Okay, but I would feel that those seeding the ocean with iron filings and things, they could have lots of unintended consequences. And same with sulfur dioxide. So I'm for a lot of the forms. I'm a little leery of the others.
If I could categorize in my mind the last 30 years of government involvement in energy, I think I'd summarize it by saying, don't just do something, stand there and argue. If you could look ahead for the next 10 or 20 years, what do you think that we would categorize government involvement both nationally and internationally?
Well, let's start with government involvement at the state level. California is a leader among the United States and one of the leaders in the world. At a national level, we're paralyzed. We don't have a national energy plan. So while states like, notably California, but New York and Massachusetts, and the majority of states actually have renewable portfolio standards. Okay, as an example. Not as, California has the most aggressive, but it's not like the United States is completely failing. At the federal level, yes, we're going to be deadlocked for the rest of this administration. We'll be lucky if Congress passes another budget. This is, So I think in the end, the United States has not been showing leadership. It has been actually been the opposite end of it. China will probably put a significant price on carbon unilaterally without a UN agreement before the United States does. Okay, and so that is something I'm doing my best to actually help China, get from here to there, in the hope that, hey, the United States, wake up. But right now, our political system, as you may know well, it's in a quasi-state or a complete state, depending on your point of view, of paralysis. And it's really unfortunate for many things. But for this one, it's really, so yes, we're not showing the leadership we should show. We're showing the leadership in technology, but it's the deployment that we're not showing. Okay.
I appreciate your positive look at the future, and especially as a scientist. You have a foot in the political world and in the scientific world. I am very concerned, and especially regarding some numbers from 350.org, which speculate or postulate that in 15 years, at the rate we're going, we will have enough carbon in the air that we will not be able to have a sustainable Earth. And could you comment on that? Because this is wonderful, this is giving us answers, but will we act soon enough to be able to provide a future for our children?
Well, there's no clear point. See, the longer we wait, the longer we woofle waffle, we the world, the bigger the hole, the deeper the hole we dig. I can't say with certainty after this point, done, it's done, you might as well go home. It was just whoopee it up because our grandchildren are going to really be in a bad state. As a scientist, I'm not willing to do this because if you do that, then you give up trying. And that's the last thing you want to do. I will admit, though, it gets harder and harder. With each succeeding year, with each succeeding decade, it gets harder and harder. Is there such a thing as being too late? Yes. I think by mid-century, if we haven't decidedly off this path, we're going to cruise to 3, 4, 5 degrees. That is just in the cards, and that is really scary because of already what we've seen in just 0.7 degrees, 0.8 degrees. And so, to quote Martin Luther King, there is such a thing as being too late. But I can't, if we go from, we're at 400 now, parts per million. We're going to, sadly, I think we're going to go over 500. Therefore, we need to be grabbing carbon dioxide out of the atmosphere with vegetation, with better crops and, dare I say, genetically engineered things of crops. And because by the way, our crops are genetically engineered. But we need to be capturing carbon out of the atmosphere because we're going to go above 500 parts per million. Okay, and so that's I don't think we're going to stop at not only 350. We're past that. But we're not going to stop at 450.
The methane, the permafrost and the methane.
Yeah, we don't know exactly when the methane, as the permafrost thaws, methane does come out. It has begun to come out, and the question is, and there's one of those tipping points. We don't know when it comes out in buckets, but it's one of those. Not it's the wrong analogy, but you know what I mean. Lots of it. We don't know at what point it's going to come out where it really becomes a tipping point, and then it's a runaway effect. And so I can't say exactly when that will be, but see, it's a probabilities. There's a probability something will happen, and the question is if there's a certain probability that and it's a very long tail, and so would you risk a 10 or 20% probability that really bad stuff happens at the 4, 5, 6 degrees? That's really non-adaptable bad. And would you, it's, another analogy is like the smoking analogy I use. We smoke, our grandchildren, their grandchildren suffer the consequences. It's Russian roulette. Every decade you put in another bullet, and you give it to your grandchild and say, pull the trigger. That's what we're doing, okay? We can debate whether there's 1 or 2 or 3 bullets in the chamber, but every decade, you know, the probability of something really bad happening is increased. And there's a point where it's a certainty that some really bad stuff will increase. We would never do that to our grandchildren. We're doing it.
I think we have time for one more question.
I'll do 2 more.
Okay, two more.
Comment on the promise and the challenge of fusion?
It's a scientific experiment. I don't know whether it will work. The trouble with fusion is that it's a huge capital investment. And so if you're talking about, you know, what's mostly sinking the nuclear industry, there are 2 things. It's certainly the fear of radiation. There's also non-proliferation effects. The waste issue is a solvable thing. But proliferation, it requires some international cooperation. And the safety, although safety is actually minor in the sense that if you look at the deaths per terawatt hour produced in nuclear versus coal, it's 4,000 to 1. Oil versus nuclear is 1,000 to 1. 1,000 deaths in oil per you know, including Chernobyl. And so, and all the estimates of cancer. So the safety is also something, but there is an irrational fear. Fusion has less long-term radioactivity, but there are materials problems we don't know how to solve yet. There's a cost issue. If it costs $10 billion to build a fusion plant, and there's a delay, it's not economically viable. That's actually what killed nuclear, is the delays and the embedded capital and the delays. And so that's one of the issues. So I just don't know, but my feeling is, in the overall scheme of things, what society should be investing in is looking at a lot of solutions. Okay. I personally think that renewable and energy storage and long-distance transmission will get there a lot sooner. Okay.
Thank you.
One last question.
Thank you very much. I was just wondering if you could comment some more on the slide you briefly showed about efficiency in land use and what factors are involved in that specifically.
Sure. Land use efficiency is really something where we can really improve upon. And our agriculture, although it's been the world agriculture, we over-fertilize with, you know, there's all sorts of issues. Land use efficiency in terms of using land to grow grains to feed us, and with a modest amount of protein or a high protein diet, with, you know, it's a 10 to 1 to 50 to 1 ratio to 4 to 1 at best in terms of land use. And so you know, that has a lot of sociological stuff with it, because no government's going to tell their people what they can and can't eat. But in terms of land use and the efficiency of land use, there are still going to be great gains. The United States agriculture is a very efficient in production. We're still ahead of most of the world in yield per acre. And so one can still improve upon that, but the fertilizer runoffs there's lots of things. Water is an issue. Everything's has becoming an issue. So the nexus of food, water, energy, they're all related. They're intimately joined at the hip. And this is the larger sustainability issue that we have to think about. California uses 22% of its electricity to move water. Okay, and it's going to get worse. It's not going to get better. Anything west of the Mississippi, the wells are going deeper and deeper. And in Mexico, deeper and deeper and deeper. You go from 50 feet to 100 feet to 100 feet. We're now around the world mining for water. and we're depleting reservoirs that were established in the last ice age. The Alaguala Aquifer, I'm not sure I'm pronouncing it right, and when it dips all the way in from Canada all the way into northern Texas and Oklahoma, down there, you're only at 10% of what it used to be. 90% gone. Okay? This is serious. It's so serious that Texas is adopting legislation. Farmers on their own land can only draw from this aquifer a certain amount. It's going to be regulated. A regulation in Texas on their own land? Think about that. That's how serious it's become. But I'm really afraid that, 50 years down the road, if we still continue on our path, we're going to be doing emergency measures where it's mostly gone. And so, 80% of the big fish in the world are gone from overfishing. This is, we are not on a sustainable path. On that happy note.